Perfect. So hi, everyone. Thank you so much for joining us for our third SEDS Online student webinar. My name is Sarah Giles, and I'm a PhD student at Columbia University. And I put together and will be hosting our talks today from 4 fantastic PhD students who will be sharing their research projects that intercept with our topic today, new insights into coastal sedimentation from the sedimentological record. I already want to go ahead and make sure we announce that we have our next webinar coming up, which will focus on exploring sediment transport dynamics from source to sink. So we encourage any master's or PhD students who may be interested in presenting, or if you know of any professors with students, make sure to let them know about this opportunity. It's great to get questions, to share your work and build collaborations if possible. And this is a great space. We also want to thank our sponsors from IAS that allow us to offer all of these free of charge. All of these resources, webinars, conferences. So we're very, very thankful for those. So today's webinar will be an exciting series, and we will have 10-minute student talks with 5 minutes of questions. The chat box will remain open, so please put your questions in with your name and your location, and I will read them out to our presenters. Again, if we don't make them all in the 5 minutes, we will return to them at the end, so your question will get answered. So with no further ado, I want to start off with our first presenter, who is Liz Mahon, a PhD student from the University of Melbourne, who will be discussing Paleocene coals and prograding shorelines. So whenever you are ready, I will stop sharing my screen and let you go ahead, Liz.
Okay.
Perfect. And I'm still waiting for it to load, so just give it. Okay, looks perfect. Go ahead whenever you're ready, Liz.
Okay, thank you. So like Sarah said, I'm a PhD student at the University of Melbourne, finishing my PhD very soon, handing my thesis in 2 weeks. So this work I'm presenting today is part of my thesis, and so it's a chapter of my thesis that we're hoping to publish in the next couple of months. So still a little bit of work to do. So I'm going to be talking about lower coastal plain coals and prograding shorelines of the Paleocene in the Gippsland Basin. The Gippsland Basin is located on the southeastern corner of the Australian continent. It formed as Australia rifted off Antarctica during the Mesozoic with the breakup of Gondwana. So the Gippsland Basin is located in between the mainland and Tasmania. And up until the mid-Eocene, there was a land bridge connecting Victoria and Tasmania and sheltering that southern margin of the basin. The Postrift stratigraphy is composed of the Latrobe group and the sea spray groups. So we're focusing on the Latrobe group today, which is predominantly made up of coastal plain sediments with very restricted marine sedimentation. The Gippsland Basin has a long-running history of industry interest. The onshore area has over 100-metre thick coal seams, which have been mined since the 1800s. Offshore has large hydrocarbon reserves, which Exxon are producing for a number of years. So the kind of upshoot of that is there's a huge amount of data in the Gippsland Basin. So we've kind of taken advantage of that, and we've used a merged 3D seismic volume, which is termed the mega cube. It's a merge of 18 separate seismic surveys. So this seismic is quadrant phase and SEG reverse polarity. So what that means is that a increase in acoustic impedance, so a shift from a soft to a hard, is reflected as the zero crossing of a negative trough to a positive peak. So I'll mention that again a bit later. And of course, there's stacks of wells in the basin, so we've used 28 key wells. So the main points of this research is that coastal systems of the Latrobe group form the main hydrocarbon reservoirs and are often referred to as deltas, and the coals are often interpreted as forming on alluvial or upper coastal plains. However, research is indicating that that's not quite right. They're more commonly being termed, the shore face more commonly being termed barriers these days. But there's still a bit of a historic bent toward the classic delta alluvial plain kind of depositional environment. So we decided to use the extensive industry data sets to interpret particularly the deeper interval where there's been less interpretation undertaken. So we've developed a stratigraphic framework, which is composed of 4 key horizons, which envelope 3 key intervals. These are termed the T8, T7, and T6, which is a pre-existing nomenclature we've carried deeper. And these intervals show a general slight decreasing thickness, with the T8 being 240 meters thick and thinning slightly to the T6. Instead of using the standard well logs, Y-line logs that come with the wells, we decided to use a electrolithography software. So the Kansas Geological Survey have a nice little free software applet you can use online called Chameleon. And it's very useful for delineating lithologies. So it takes the rock property values from those Y-line logs and applies a 256 cubed color cube to those values, and you get something like this. So as you can see, it's delineated our lithologies really nicely, and in addition, it's shown some really nice trends and patterns of the way those lithologies are appearing. So of course, we correlated our electrolithographies with core, and it confirmed beautifully those interpretations. And in addition, there's some nice kind of little sedimentary structures visible in the core. The focus was the coal. So the number of coal layers increases up section from the T8 to the T6, despite the fact that the total unit thickness is decreasing up section. Although the T7 had the lowest total coal and the thinnest coal seams. The coal seams seem to range from 0.4 to 7.1 meters, with that 7.1 meter seam marking the top of the T8. So it's a really nice horizon to run some extractions, which I'll show in a minute. We developed a very broad seismic facies scheme, with seismic facies 1 consisting of fairly parallel and continuous seismic reflectors, seismic facies 2, sigmoidal cliniforms, seismic facies 3, fairly parallel and very high amplitude seismic events, and seismic facies 4, quite chaotic and discontinuous seismic. And also of focus was seismic facies 2, which is our lovely progrades. So you can see the progrades display quite an accretionary character. So they transition from roughly 1/4 to 1/3 of the total package size all the way up to the whole package size. The T8 displays the most progradation, so on average 14 kilometers. The T7 displays the less well-developed progradation, and in addition, it had the least coal, so that may be reflecting some instability in the system and perhaps more flooding events. Additionally, the progrades appeared to vary in character from the northern part of the Central Deep to the southern part, so they were better developed in the southern part of the Central Deep, and that may be reflecting some of the interplay of sediment supply and a combination space with growth on the normal bounding faults in the basin, as it was sort of in a waning passive sag phase with a little bit of extensional growth behavior. So we integrated our seismic and electrolithographies and found that seismic facies 1 correlated very nicely with our mudstone and siltstone lithophases. So the well on the right, Helios 1, displays that interval. In addition, well completion reports reported a lot of dinoflagellates and some glauconite. So we've interpreted that as our condensed marine interval. Seismic facies 2, with those lovely progrades, correlated to these very thick, clean sands and some siltstone, which we've interpreted as a prograding shore phase. And then seismic facies 3, the very bright seismic events correlated very nicely to coals, which were interbedded with the other lithologies, sandstone, siltstone, mudstone. And then as you move toward seismic facies 4, those coals seem to reduce significantly. We lose that really bright seismic amplitude. Coals are still present, but in a lot less of them. And the sediments tend to be dominated more by sandstone and siltstone. So this is, we ran a lot of seismic extractions. This is my favorite. This is a maximum negative amplitude extraction on the top T8, so H2 on that little diagram at the top. So this is our 7.1 meter coal, which is on this seismic, coal appears as a negative seismic event, so maximum negative amplitude of a negative event. On this extraction, the white is coal and the darker colors are siliciclastics. So straight away, you can see there's a lovely arcuate paleo shoreline that extends for well over 100 kilometers. This is quite a large extraction area. In addition, we can see sets of parallel strand lines indicating strand ridge planes or beach ridge planes. And we can see that the coal is concentrated immediately behind the shoreline. The coal is cut by a distinct network of meandering and branching fluvial channels. And then as you move landward, you lose a lot of that coal signature and you're moving into a more fluvial dominated coastal plain. So this is a zoom of just the center of that extraction for a bit more detail. And you can see the meandering channels are showing even little coal islands in between the meander cutoffs. We see distributaries, we see thick meander scrolling, and in between it all, we see this very complex character to these coal-rich areas in between those branching channels. And this is a pattern that we do see elsewhere in the world. So in the Rajang Delta of Sarawak, we have these lovely irregular shaped peat islands in between these meandering branching channels. The Rajang Delta is known for its ambrogenous peat deposits. That is, they are built up above the water table, so they're reliant on high rainfall. So we suspect that this is kind of consistent with what we're seeing in the Paleocene in the Gippsland Basin, saying that there's probably also planar peats as well. We don't think it's necessarily all ambrogenous peat domes, probably a combination. But there has been work done on younger coals in the Gippsland Basin, which have shown that they are also ambrogenous. So it's possible that it's sort of a feature of this basin. The caveat being that the Rajang Delta is, of course, a delta, which we don't think we have a deltaic shoreline here. In addition, it's probably got a little bit more tidal influence. So we have a more wave-dominated shoreline with those lovely strand plains. So this is a kind of a general depositional model we've put together of the strand plains. The kind of domed peat deposits, probably some planar peat deposits as well, which may be occurring at the same time or at different times throughout that whole Paleocene. And then that complicated network of branching and highly meandering channels. Thank you.
Excellent. Thank you so much, Liz. And so while we wait for some questions to come in the chat, that means I get to ask you mine first, Liz. And something I'm wondering is, you briefly just mentioned for the analog, it's tidal dominated, whereas yours was probably fluvially dominated. How do you think that might change some of the coal characteristics? And if it was wave dominated too, what might be some of the expectations for those?
Yeah, I'm not sure it's having a huge impact. So we see the coals are actually growing right up to the shore face. They're actually in between the strand plains and in fact been cut by the strand plains. So I don't know that it's impacting the coal development too much. Yeah, I think because potentially for that ambrogenous kind of topographically higher peat development, it's a little bit more self-protected from any kind of marine inundation that might come with higher wave energy or large tides, I guess. Yeah.
And so I'm sorry if I missed it, but do you have any cores to look at from where you've been looking at the seismic at all?
Yeah. I showed a little one earlier on. We have a little bit of core. I would have liked to have incorporated more core, but unfortunately, all of the core is in Western Australia, which has some of the tightest borders in the world with the pandemic right now. And I'm in Victoria, so I definitely can't get there.
Okay, and do you think that would help with any of the interpretations you've been making, seeing if there's any types of structures or mass flow in certain locations where it's more organized? Would it help at all, do you think?
Probably more if I wanted to refine my interpretation to a little bit more finer detail. We know that there is tidal influence. It'd be nice to capture how much. We could probably do more analysis on the coals themselves, looking at ash content and sulfur and marine inundation and that sort of thing. So that's probably a future work aspect.
Well, that sounds fantastic. So you have a couple questions coming in here. So the first one is from Gary Hansen, who says, "Hi Liz, really nice work. Thanks for sharing. Are the channels fixed in position and vertically A grading? anastomosing, or do you see evidence for lateral migration? And this is Gary from London.
So the channels are not, so the resolution of the seismic isn't great. I should have said that at the start, particularly in the Paleocene. So on the seismic, it tends to be only, the most resolvable channels tend to be only at most a wavelet or two. So it's difficult to get a sense of exactly how much kind of lateral or vertical behavior is occurring. My impression is that they are, while they display like really beautiful meander scrolling, they themselves are not super aggradational. I think, as particularly if the peat is building up, that might be a element of restriction on that channel behavior. Saying that, I'm speculating a little. Yeah.
Awesome. Okay, so we'll ask one more question and then we do have to jump on, and any questions after that we'll either send to you, Liz, if you have to leave because it's 2 a.m. for you, or we'll return at the end. So the next question is from David from Houston, Texas. He says, really cool work. Did you notice any lateral variations in coal concentrations? Is there any relationship between the distribution of more developed section of cliniforms and the distribution of coal?
Yeah, so the T8, so the basal unit, does display both the nicest well-developed cliniforms and the thickest coal. So there may be definitely some interaction there. Perhaps the shoreline is better developed and more stable, and then protecting that lower coastal plain aspect. It could also be as simple as just less marine inundation or a more stable climate at that time. There are lateral variations in the coal, definitely. The thickness does vary, which may be a factor of that androgynous character. Also, the shift from domes to planar peaks. I suspect that is happening simultaneously as well as through time. But I'm sort of got a little bit more work to do on that aspect. I need to do a little bit more reading, I think.
Well, thank you so much, Liz. It was a fantastic presentation. You do have a few more questions, so we'll resolve that in the end, how we want to distribute them. But thank you so much for being up at 2 a.m. And we will now transition onto our next talk, which will be from Kat Wilson, who is a PhD student from the University of Texas at Austin. And she'll be discussing what we can observe in lithified coastal dune morphology. So Kat, oh, perfect, you're ahead of me. This looks great, go ahead.
Okay. Hi, everybody. Thank you. Yeah, so today I will be discussing some of my PhD work on the erosional signatures of marine transgression preserved in lithified coastal dune morphology throughout the Bahamas. So the Bahamas are really an interesting place to study past sea level cycles because they record periods when sea level was higher than modern, but also because the platforms are quite shallow. The islands and the shallow marine sediments on the platforms are exposed when sea level drops just a few meters below its current depth. The subaerial topography on the islands is largely constructed from windblown dunes, and so there's active Holocene dunes near the modern shorelines, and late Pleistocene dunes construct most of the area and topography of the islands. In some places, they reach over 50 meters above present-day sea level. The dunes are stabilized through carbonate cementation, and they're also currently very heavily vegetated. But that cementation has resulted in unique preservation of the landforms from the last few interglacial cycles, especially unique preservation compared to siliciclastic systems. So until we had high resolution DEMs widely available, most of the studies were limited to road cuts and shoreline exposures, but now we can analyze and interpret the coastal dune morphology at an island to regional scale. So I want to highlight that my two primary study areas have been Eleuthera and San Salvador, and all of the data I show today have been generated from those two islands. Both are on the windward or eastern side of the archipelago and are subjected to a lot of wind and wave energy from the open Atlantic Ocean to the east and to the north. So digital elevation models have revealed the extent and variability of dune ridges across the region. And a valuable characteristic of these aeolian dunes is that when they were active, or when coastal dunes are active, they're extremely sensitive to environmental controls. So the presence of dunes inherently means there's a sediment source and a wind climate capable of moving sand into the dunes. And the topographic relief and the shape and form of the dunes are a product of the sediment supply and surface properties and the wind conditions at the time of formation. But most important to this work is that coastal dunes record a relative sea level at the time of formation. Because the dunes are terrestrial landforms, they are an upward limit on the paleo shoreline position and sea level. So the sensitivity of dunes and the widespread occurrence throughout the Bahamas can help us answer some outstanding questions and connect the evolution of the landscape to kind of broader climatic and environmental forcings. So one of the questions is, when were these dunes active? They've been linked to the marine isotope stage 5, which was between 130 and 80,000 years ago. But this is a period of 50,000 years, and constraining their age within this stage remains challenging because of limitations of radiometric age dating in these systems. And so without knowing the exact age of the aeolianites, we can't simply link the morphology to available sea level curves. So we're still left asking, what was the sea level at the time of dune formation? Coastal dunes source their sand from the adjacent beach. So at least at the beginning of development, construction of the dunes, the upwind dune toe will be pinned near sea level. But after that, dunes can either remain beach attached or be disconnected from the shoreline by landward migration, or alternatively, the shoreline can regress away from the dunes and separate them from those marine processes. So recognizing the geomorphic signatures of coastal dunes remaining beach attached and subject to marine erosion would be a reliable indicator of shoreline position. So we can do this through recognizing scarping. Scarping occurs when waves attack an unconsolidated to weakly consolidated dune and results in a steep upwind face. The scarp originally can be subvertical and then relax through time through slumping. And scarping can occur for hundreds to thousands of meters along shore, as this example from Eleuthera shows. And the height of a scarp is a function of initial dune height. In the Bahamas, the Holocene dunes, at least, are commonly above 10 meters. Here I am standing next to one in San Salvador, and then my advisor, David Bührig, and our rental car is actually sitting on the top of this scarped Holocene dune. In the background, there's a slight dip, which is hard to resolve from the photo, and then the Pleistocene aeolianites form that large ridge in the background. So these examples can be used as analogs from the Holocene to help us understand similar erosional morphology in Pleistocene dunes throughout the region. So here's an example of a paleo dune scarp that's resolved in a digital elevation map with a contour map superimposed. The Pleistocene dunes with paleoscarps are no longer in contact with the modern shoreline due to later Pleistocene and Holocene accumulations on the upwind margin. But the scarps are preserved as very steep and continuous alongshore linear features on the more energetic Atlantic side of the dunes. The interpretation is that the dune was subjected to frequent marine erosion and was pinned at the shoreline before the dune was fully cemented. So we've used multiple metrics to identify paleoscarps across Eleuthera and San Salvador from these DEMs. The first that we've used is slope angles, and here we show examples of a paleoscarp in black and then an unmodified dune in lavender. We call the unmodified dunes anything that, well, they don't show the morphologic signatures of post-depositional erosion. So our interpretation is that the unmodified dunes became separated from the shoreline and they resemble transgressive dunes. We extracted slope data to polygons which circumscribe the upwind and downwind faces and produced millions of data points across the two islands representing the scarped faces, unmodified and lee slopes of these dunes. And in the cumulative distribution curve here, the unmodified dunes have much lower distributions. Their means are around 4.4 degrees, whereas the scarped and the lee faces have very similar distributions with means of about 9 degrees. So we attribute the similarity of the scarped and lee faces to processes of grain flows, collapse of the steepest portion, and then diffusion of the slopes over time, which lower the slopes to an equilibrium angle on both the scarps and the lee faces. So the next metric that we use are dunes is symmetry, is using a slope ratio. So to do this, we averaged all the slopes on the upwind side and all of the slopes on the lee side, and then divided the upwind by the lee, stoss by the lee. And here we have a couple of example profiles. The gray is a scarp dune and the non-scarp dune is again in purple. And you can see that in the form and in profile, the non-scarp dune has secondary bed forms moving up the stoss side. They tend to be wider and lower angle on the upwind side, whereas the scarp dunes are have a smoother face, steeper, and they have a much more symmetrical profile. And this is quantified by this ratio where the unmodified dunes have slope ratios commonly below 1, whereas the scarped dunes tend to equal or exceed 1, quantifying that symmetry. And then the third metric is sinuosity in the alongshore direction. This is really clear when we look at these forms in map view. You can see an example of a sinuous, or what we're calling unmodified dune form, compared to a scarp dune form. But we wanted to quantify this property on both the upwind and the downwind side of the dunes. So the scarp dunes on the upwind face have lower sinuosity values, below 2, all the values are below 2, compared to the unmodified dunes, which have values as high as 6 for the sinuosity. The lee faces don't show a clear pattern of difference between the two dune types. And this is because the surface properties and the migration patterns affecting downwind morphology are expected to be the same between scarped and unscarped dunes, because that erosion is really limited to the seaward or the upwind beach attached side of the dune form. So these three metrics seem to be reliable properties to recognize a paleoscarp in coastal dune morphology. The upwind slopes averaging 8 to 9 degrees, a slope ratio being close to or above 1, and low sinuosity are characteristic of paleoscarps. And commonly the truncated or paleoscarp dunes tend to be more narrow than the unmodified dunes that we see in the topography. So from this work, we've interpreted that dozens of Pleistocene dunes have preserved paleoscarps on their upwind faces. These scarp dunes were eroded as loose sand to weakly consolidated dunes rather than fully lithified, which would have formed steeper cliff type morphology. The dune forms are particularly valuable as terrestrial limiting indicators of paleo shoreline position, because the dune front not only indicates a vertical sea level elevation, but also lateral positioning of that shoreline, which together gets at a more holistic understanding of the regional transgression, especially in places like San Salvador, where some of the paleoscarp dunes are several kilometers landward of the modern shoreline. So with increasing global availability of digital elevation models, we think that these morphologies can be used elsewhere to interpret evolution of dunes, improve regional understanding of shoreline position, and provide a benchmark for things like paleo shoreline sea level models. So thank you very much for your time and attention. I'd be happy to take questions.
Thank you so much, Kat. That was fantastic and incredibly interesting. So I'm going to start us off with some questions while we wait for everyone else to post them in the chat with their name and location. And so, Kat, I'm wondering, is there any way to use grain size at all to identify these scarped versus non-scarped dunes? You talked wonderfully about the sinuosity and the lithification, and this may be beyond the resolution of the DMs, but maybe with some field work, is there any grain size indicators at all?
Yeah, so that's a great question. It's certainly, I wouldn't know how to approach that with remote sensing data, but we have done field work in the region, and the grain size is very consistent regardless of the morphology or kind of the surface topography of the dunes. It's all kind of a upper fine sand, kind of characteristic aeolian. It's really hard to distinguish, yeah.
Okay, okay. And so do you know, if you were thinking about these DEM models, you know, you were talking about how you typically do get to do field work, but you had to shift and adjust to COVID. How do you think these have enhanced some of the findings you've had?
Yeah, so a lot of this work would not be possible without DEMs because the islands are so heavily vegetated that unless we have road cuts or outcrop exposure at the shoreline, it's really hard to get a sense for the scale of the relief or any of the variability across the islands. It's very challenging. So this has really changed the way that we can study these systems.
Gotcha. So we have a question here from Val who says, super figures, Kat, how different is the paleo wind direction in your figure from today's dominant wind direction?
Yeah, that's a good question. There's reasons to believe that it's pretty similar. The dominant wind energy is coming off of the Atlantic, and a lot of it is associated with the trade winds. So between modern wind climate and the Pleistocene, it's likely that it's more similar than different.
I have a question again for you, Kat. So I work in the Ediacaran, so we don't have any plants to hold down, you know, our dunes and things like that. You said you have lots of plants on the Bahamas. So if you were just going to speculate, and no worries if you're not sure, but how do you think not having plants might change some of the scarp and geomorphology that you're seeing?
Yeah, so that's a great question. I think that not having vegetation as a way to stabilize the dunes and arrest their migration across the landscape, they're more likely to get away from the shoreline. I think some of my other work has really investigated how surface properties affect the morphology of the dunes, and in a lot of these dunes that remained beach attached, it's expected that they were that they had a backstop in a way, that they weren't able to run away, because there's other dunes in the region that are much more transgressive and they seem to have migrated kilometers across the platforms. I didn't have a chance to talk about that during this talk, but there's quite a bit of variability there. So I would think they'd be much more mobile.
Gotcha. And so we have a question here from Catherine Maxwell who says, nice talk, Kat. Maybe I was not able to catch it, but what did you sample to derive the age of the Pleistocene dune? Thanks.
Yeah, so that's a great question. Nothing from my work has tied the dunes specifically to the MIS5, but there's been many other researchers that have worked in the region for a long time that have associated these landforms to both MIS5 and old, and in some places older than that. So that's building on past research, not necessarily my own.
And so we have one more question before we'll move on. This is from Maria Jensen, who asks, how about wind strength during the time of deposition relative to today? Are the dunes assigned a more windy climate?
Yeah, that's a good question. It's hard to say because there's a wind climate that the current wind climate is capable of building dunes. There's they're volumetrically smaller in the Holocene, but there's maybe a lot of questions for that, whether that's about sediment supply or things. So it's really hard to say about wind strength. We know that there was enough strength to build the dunes, and I don't want to speculate too much more than that.
Well, fantastic. Thank you so much, Kat. Your DEMs are beautiful, and thank you so much for presenting to us. And we will move on to our third presenter, who is going to be Yannis Kappelmann, who's a PhD student at the University of Bremen, and he will be discussing reef islands in Southeast Asia. So whenever you are ready. Perfect. Looks good. Get started, Yannis.
Yeah, thank you, Sarah. As the title implies, I'm going to introduce to you the research that we are doing on reef islands from Southeast Asia, and say something a little bit about how they developed over the Holocene. So just to quickly introduce you to these landforms, these reef islands are usually pretty shallow. They exceed the mean sea level by a few meters, maybe only even by a few decimeters, and they are usually forming on top of reef complexes, meaning that they may form on top of barrier reefs, or as in this case here, on top of a patch reef, where the actual island is located in the west of the complex. What's also characterizing them is that they are usually consisting of reef-derived carbonate, meaning that when we look at the sediment from the actual island body, we see skeletal remains from maybe corals, coralline algae, gastropods, or so on. So these islands in general form important habitable space around in several regions around the Earth, and therefore some questions arise about the future stability when we think about ongoing environmental change and also sea level rise. So regarding the stability of these islands, there are two major boundary conditions that are considered to govern the formation as well as the stability of these islands. And one of them is the material supply. So the sketch on the upper right side here sums it up pretty good. There's a lot of dynamics going on in the surroundings of these reef islands, maybe a constant erosion as well as accumulation. And if we imagine that with ongoing environmental change, there may be some deficits or alterations in the sediment production, this will of course also have some effects on the actual island. What this sketch also implies is that these dynamics are usually governed by the hydrodynamics, which is the second boundary conditions. So these islands are constantly evolving and maybe also, as in this instance here, may change their morphology in accordance to, in this case, the monsoon. Coming to the motivation for our study, the study area that I will introduce to you in a few seconds has hosted, so to say, a study in 2017 in which the authors have investigated in Reef Island and compared the surface sediments to the subsurface sediments, so down to around 1 meter. And what they found was that the subsurface sediments were mainly composed of coral fragments, which is in strong contrast to the surface. So the most recent sediments appear to be mainly composed of coralline algae and at the same time lack coral fragments, which appears or maybe an indicator of an ecological shift. So that's where our study basically comes in. And one of our questions was, how did the supplying ecosystem develop over time? However, as this webinar is more focusing on the insights into coastal processes, I'm going to set the focus a little bit onto the physical background on the physical components of our study. So what kind of constructional processes can we infer, and when did these occur in general? So as promised, coming to the study area is the Spamonde archipelago, which is located offshore Sulawesi in Indonesia. And if we look at this map here, we can see that it's a pretty broad carbonate shelf, and at the same time pretty shallow. So the maximum depths on the outer shelf here are around 50 to 60 meters. And there are several reef structures and also some reef islands marked in black here. This shelf is under strong influence of the monsoon. It experiences a strong southeast monsoon and a weaker northwest monsoon. And the island that I've just talked about with the implied shift is located here. And our actual island that we have chosen for our study is just south of that, and another mid-shelf island. And marked by the axis here on this landform, you can see where we have drilled our course. So that's what we basically did. We did core drilling down to 10 meters below sea level, below island surface, not sea level. And we have sampled in 1 meter intervals in order to say something about the sedimentological development there. I said I don't want to get too much into detail regarding the ecological background. What I can say is that we have observed a pretty homogeneous skeletal composition, and this all mirrors, so to say, a transported material, whereby we were able to hypothesize or to say that the actual island is superimposing an infill lagoon. And we have used the skeletal composition as well as the mean grain sizes for cluster analysis. And as I said, the skeletal composition was very homogeneous. Therefore, these clusters are mainly differentiated by their deviating mean grain sizes. The rectangle width here is indicated for the mean grain sizes of the respective samples. And when we see when we take a look at the spatial distribution here, we can see that there are very coarse deficits, especially in the west as well as in the east, in the lower sections. And these are interpreted as, to originate from high magnitude events. Of interest is that when we look at the central core, the corresponding depth, so the deeper strata here has significantly finer sediments, whereby we may assume that the supply of sediment was generated from both flanks, so from the west as well as from the east, in order to infill this lagoon. Now coming to the really interesting part, so to say, the radiocarbon dating. We have selected some samples for radiocarbon dating, and I would like to draw your attention to these calibrated radiometric ages. And what occurs is that we find the oldest ages of our samples to be around from around 7,000 years ago till around 6,000 years ago in the West, whereas the majority of the sediment of the other samples appears to be of a significantly younger age. Like maybe around 3,900 years before present to 3,200 years before present. And also the actual island body appears to be of a similar age as the underlying strata. So we've used these radiocarbon results in order to set up an information model, so to say, as I said, infill of a lagoon. And these very initial samples, or these sediments that we have observed there, appear to fall into a time frame from which we know that the southeast monsoon in the Indonesian area has reached its maximum intensity in the Holocene. And this time frame covers the time from 8 to 6,000 years before present, and subsequently the intensity of the monsoon declined. And when we look at the data furthermore, we see that there appears to be some kind of pause, a hiatus in our sedimentary strata, which may be explained by the decline of the monsoonal energy. But also when we look at the sea level curve, or the sea level data from the study area, we see that around this time of the hiatus, the study area has experienced a slight sea level high stand of around 50 centimeters. It's a bit scattered here and a discontinuous plot, but there has been some kind of a high stand, and it appears that we have no strata from this time. After that, the sea level declines and falls to the recent sea level, and the majority of our sediments, or of the infill that has taken place, appears to fall into the timing after the high stand has ended. So later, or going towards the modern time, the next stages were characterized by island growth, by island accretion, so to say, and the subsequent stability of the actual island. And when we now compare this to some other reef island models, we can discover some similarities as well as some differences. This is a model from New Caledonia, and Reef Island from New Caledonia. And what's of similar nature as in our study is that once the formation or once the reef flat provided an accommodation space for the actual reef island, the formation of the island occurred rapidly, which is pretty similar to what we have discovered. However, some studies exist from the Maldives, and here it's of slightly different nature. We see that some reef islands have built it as a consequence or during a sea level rise, or during high stand periods, which is also in contrast to our study, because we do not observe any data from the high stand times in the Spermondum. And also there are some models that have implied that the decrease of sea level has led to the accumulation of a reef island, and also this hasn't been the case in our study, because we see that the sea level fell to the actual recent position has rather or is rather connectable to the island formation of our study. So just some conclusions here. We see that the initial lagoon infill was promoted by a stronger southeast monsoon from the early to mid Holocene. We have observed a hiatus, which apparently falls into a time frame from which we know that the monsoon energy has declined and that there has been a sea level high stand. And we see that the actual infill and the island formation occur very rapidly after the sea level has fallen from its high stand of around 50 centimeters before or above the recent sea level. So overall, this is the first comprehensive model that shows how monsoon and sea level fall have governed lagoon infill and thereby generated accommodation space for a rapid reef island formation. And with that, the only thing I want to do is to say thanks to the DFG for funding our project. Thanks to the Hassanuddin University in Makassar for providing assistance in the execution of the fieldwork. Thanks to Dominic Kner, who actually did the fieldwork, who drilled the island. Of course, also thanks to the great work group that I'm affiliated with, the Geoecology and Carbonate Sedimentology work group at ZMT. And a special thanks, of course, to my great supervisors, Hildegard and Thomas, who allow me to do this very interesting research. And with that, I would like to come to the end, and I'll be happily discuss or answer some questions now.
Thank you so much, Yannis. That was fantastic. And so a question I have while we wait for some questions to come into the chat is, did you look at any of the isotopic work or have any kind of general framework there? Would the incoming monsoons that are introducing a bunch of rain and new rainwater into the system affect some of the carbonate material that is available, some of the ecology, or is that generally not something you can measure and influence from?
Not in this case. Even though there is some monsoonal influence on the shelf, it's basically just the wind, because there is some terrestrial influx or some fluvial input to the general shelf. However, it's pretty limited, and it's not thought to really reach the ecosystems of the island that we have investigated here. It reaches the near shore islands, but not the mid-shelf, apparently.
I see, and you had showed that there was some sea level fall. Did you see any type of erosional effects from that at all? Or it typically seemed like it led to more island formation rather than taking away any material?
Could you repeat the first part of the question? I did not really get this, sorry.
Yeah, no worries. I was asking, you said that there had been, a relationship between sea level fall and your island formation. And I'm just wondering if with that sea level fall, there was any erosion of any sort, and did that affect the island formation at all?
Yeah, well, we did not observe any in our sediments, and this is also of contrast to some other studies, because some studies have shown that, especially in the supplying ecosystem, a sea level fall may lead to, of course, some ecological shifts as well. So the example that I've shown to you from New Caledonia, this apparently has reported some changes in the skeletal composition. However, we could not we could not observe any in our study, and we were only able to connect it to the sea level fluctuations once we have once we received the radiocarbon analysis.
I know those radiocarbon dates are so cool. We have a question here from Ross Campbell, and then we're going to move on, and any other questions in the chat we'll revisit as a panel at the end. This says, great talk, Yannis. Do you think most of the island building is related to storm events? And this is from Ross from Canada.
Yeah, that's a good question. Well, the actual island formation, I guess it's rather connectable to moderate energetic events. So as we have seen, or in this study that I've mentioned regarding the strength of the monsoon around 8,000 to 6,000 years before present, has clearly shown that there has been a clear decline in energy since then. So I therefore assume that the storm, the influence of storms hasn't been that much of a factor in this case here. However, there are some instances for reef islands in which storms have apparently had a huge role in the formation of these islands.
Thanks so much, Yannis. You have a couple of questions coming in, and I promise we will visit them back at the end, but just to make sure everybody gets the right amount of time. Thank you so much, Yannis. And we will move on to our final, but definitely not our least speaker, who's going to be Laura Bührig, which is a PhD student from the University of Leeds, who will be discussing a database approach to source-to-sink models. So Laura, whenever you are ready, please start sharing your screen.
Yes, just a sec. Okay.
Perfect, looks good.
So I will just stop the video because my internet connection is not so stable. I will turn it on later. So hello everyone and welcome to my talk. I'm Laura, and in my presentation I will share with you parts of my PhD project regarding the role of the shelf in shaping submarine canyons and shelf edge deltaic systems. Sedimentary and hydrodynamic processes, the configuration of the continental margin, and external controls like climate and tectonic setting are all factors thought to influence the evolution of sedimentary systems. Previous studies have demonstrated that different sedimentary systems along the source-to-sink system transect, including rivers, incised valleys, or submarine fans, share scaling relationships in terms of their geomorphology and geometry of sedimentary deposits with attributes of the source-to-sink system and the environmental setting. So in my PhD project, I investigate scaling relationships of shelf edge deltas and submarine canyons with parameters of their environmental setting in a source-to-sink context. And my aim is to increase our understanding of the factors that contribute to their geomorphology and their sedimentary record, and use these insights to improve existing source-to-sink models. To achieve this, I have conducted 2 global meta-studies and used a database approach. So for my first project on shelf edge deltas, I have quantitatively investigated the geometry, architecture, and facies properties of shelf edge deltas in over 40 deltas of Permian to late Quaternary age in context of their paleoenvironmental setting, including aspects of the hydrodynamic process regime, margin type, bathymetric setting, and paleolatitude. Yeah, so here you can see an overview of the case studies that I have. And I decided to focus on the sedimentary record because in modern present day times, shelf edge deltas are very rare because usually they are intimately connected with low sea level stands or high sediment supply. So on the other hand, for my submarine canyon studies, I was able to investigate modern canyons. So I have assessed the geomorphology of 295 submarine canyons with present-day expression on the seafloor in context of the associated source-to-sink system and environmental setting. Yeah, and as here I also show the overview of the different case studies that I've used. So information on those systems and on the environmental setting I have extracted from high-resolution outcrop seafloor and seismic data sets from the literature and from open source worldwide bathymetry. And I have coded the data in form of attributes. This I did to standardize them and to enable statistical analysis. So for my studies, I have conducted different types of statistical analysis. And since some of you might be more acquainted with these than others, I will provide you with a brief summary of the methods and illustrate each with an example from the study. And hopefully I can convince you that statistical analysis don't necessarily need to be boring at all or intimidating. I find them very useful, and so I thought I'd just give a short wrap up of the different methods. So first of all, we have descriptive statistics. And for each study parameter, I have computed these from their frequency distributions in terms of the minimum, maximum, mean, and median values to identify tendencies in their range and order of magnitude. So here you can see the results for canyon morphometrics, which I'm just like showing in box plots. And then you can always see where the average values lie and the minima and the maxima. So we get an idea about the variability of values we might have and how wide the range can be in values. We can then compare frequency distributions of the same study parameter, but as a function of an external parameter, for example, to investigate whether a certain setting or environmental factor exerts control on it. So this can be achieved by hypothesis testing, which is a method to evaluate whether differences in mean values are statistically significantly different for tested parameters. I have chosen a confidence interval of 99%, which means that for comparisons of mean values, where p-values, so these are the ones that we compute in the end, are equal or less than 0.01, the difference is interpreted as statistically significant. So in this example, we have maximum canyon width, and I computed this for active margins and for passive margins. And as you can see, the mean values are almost identical, which is reflected in the very high p-value we have here, which is almost 1. So this means that we reject the hypothesis that the maximum width is on average significantly different in canyons as a function of the margin type. So the statistical test we use is called Wedge's t-test, for those of you who are interested in that. So the test we did is correlation analysis, and this allows us to assess scaling relationships between two study parameters. Correlation coefficients provide information about the type and strength of correlation. So here we have two different correlation coefficients. So the first one is Pearson's R, and this helps us to identify linear relationships. And the other one I've had a look at is Spearman's rank correlation coefficient. And this provides information whether a relationship might be monotonic. And again, I've chosen a confidence interval of 99%. So when we look at the p-values, when we compute the results, if the results are below 0.01, the results are statistically significant. So in this example of the results, we see that length and width in delta lobes and in delta complexes show relatively strong scaling with each other, and that the relationships are statistically significant. Since for the shellfish data project, I worked with the sedimentary deposits, I extracted informations from the literature, from seismic data and from outcrop data. And here, of course, we have a problem which we might not have with submarine canyons, because we have a very good spatial control on modern system. But of course, as you know, when you go to the field, depending on your outcrop situation and on the level of tectonic overprint or displacement, information might be limited. So to account for that, I've distinguished between different types of measurement. So you can see an overview down here. So when we're very lucky, we get the maximum value of an architectural element like a delta lobe or a delta complex. Sometimes it's not really clear where the flow direction is of the sediment routing. So in that case, we might have apparent values because this is a true value, but we don't really know if it's really along the axis and represents the maximum value. And sometimes, or quite often when we go to the field, we have partial values. So in a good case, we know one boundary, but maybe not the other. But very much often the values are unlimited. So we know the minimum extent, but not the true value. So to account for that, I differentiated between all these different types of values and then plotted the data. So of course, we still have some type of uncertainty because of that. But still we gather a lot of information by just knowing about the minimum width, for example, of a data lobe. So I just talked already about some limitations of these type of studies. So in general, quantitative meta-studies allow to investigate aspects of sedimentary systems on a global scale and between different sets of environmental controlling factors. So this gives us the opportunity to assess whether relationships are universally recognizable or whether they are tied to specific controls. However, due to the nature, meta-studies might carry data errors from the literature into the dataset of the meta-study if they are not identified. So I have aimed to minimize this source of bias by solely considering data from peer-reviewed publications and from government agency sources. And similarly, geographic bias in the research landscape might also be introduced in the study, which I try to reduce by compiling globally balanced data sets. Some environmental factors are constant over the window of observation. For example, whether the oceanographic environment is an open sea or a semi-enclosed sea, but others might change as the hydrodynamic regime or the position of a canyon relative to the shelf break. So similarly to what Yannick says, so my entire research project covers more than the shelf area, but because this is about the transition from the catchment to the shelf, I focus with the results I'm going to present on this part. So we all know that shelves are very complex in different regards. So one of them is sediment routing. We have a cross-shelf sediment transport from terrestrial hinterlands, but we have also a long-shelf transport by shelf currents. We have shelves when we have accommodation space, where we have sinks, where sedimentary is just like brought to a halt. So we don't have the imprint from the terrestrial hinterland to the deep marine sea. And then we have other hydrodynamic processes, as for example, tidal processes or storm events, which can complicate the sedimentary deposits by overprinting them. And we find then this when we look, for example, in outcrops. So here are some of the results from the two studies, which might contribute to a better understanding of the role of the shelf in the evolution of these systems. So although we have fewer data on shelf edge deltas interpreted by the authors as deposited under a mixed process regime, this means like fluvial and, for example, tidal and wave influence, the dimension exceed by far those recorded for shelf edge deltas in fluvial dominated regimes, as you can see here. So the results indicate that margins associated with mixed process regimes might promote greater dimensions in shelf edge deltas than river-dominated margins. So here we have a positive monotonic relationship between shelf width and the length of the shelf edge delta. And this reflects how fluvial systems that have traversed shelves to the margins develop shelf edge deltas. However, on the other side, river length itself does not scale to the length of shelf edge deltas. And one reason why this might be is that the steepness of the upper slope might inherently delimit shelf edge delta length. So we just have like continued delta front failure and it cannot develop any further. In comparison, canyon length scales weakly with fluvial system length, but the correlation strength is significantly higher for canyons in active margins, where we see moderate scaling. And canyon length shows weak but statistically significant scaling with shelf width in both margins. So here again, we have to think why we find this. And one reason might be that generally in active margins where we have the tendency to have narrow shelves and also steep shelves, that sediment is more immediately transported across the shelf to the continental margins, while in passive margins, we might have very wide coastal plains and sediment is just like deposited there for a longer time, and it takes time until it's remobilized again. So during our short window of observation in modern canyons, we might just not see the response in canyon geomorphology. So currently, I bring the results from the two studies together with the aim to refine existing source-to-sink models. I will compare the findings from the two studies to assess where we have commonalities and where we have differences in scaling with environmental factors. And this will hopefully aid us to achieve a better understanding which controls determining whether shelf edge deltas and submarine canyons involve concurrently or individually without the presence of the other, and how they might influence each other's evolution and resulting geomorphology. So for example, the vicinity of shelf edge deltas is thought to lead to a substantial increase in width and depth of pre-existing slope gullies, which can represent the early stage of a submarine canyon. So here, just like the references of the publication from which I've shown selected figures. And for those of you who would like to learn more about scaling relationships in source-to-sink systems and the database approach that I have used in my project, here are a selection of papers which provide a good introduction into the topic. So the open source bathymetric data that I have used can be accessed via the homepage of the National Oceanic and Atmospheric Administration, NOAA. So for those of you who don't know that yet and would like to try that out. And for statistical analysis, there are different programs, and I've used Minitab. And if you would like to give it a try, you can download a 30 days trial version online. And they also have a very useful online manual. So I'm currently in the process of writing up my findings for publication. In case you have any further comments, ideas, and questions that you would like to share with me, I'm looking forward to an email from you, or you can connect with me on ResearchGate or LinkedIn. Yeah, thank you very much.
Thank you so much, Laura. That's so cool. And you have such a comprehensive study. And while we wait for questions to come in, I was going to ask you, or rather beg you, that you apply some of this to river systems and do the comparisons with submarine canyons, because I look at ancient ones, so you don't have plants or animals back in the Ediacaran, and we're trying to figure out if a canyon was fluvial or submarine, and having some of these comparisons on canyon length, thalweg depth and continuation would be fantastic to compare them and apply those. So this is amazing. It's more common than you should apply to river systems.
Okay, no, thanks, Sarah.
We do have a question in the chat from Gary Hampson, who says, "Hi, Laura, thanks for a very interesting talk. Do you have enough data to test whether there is a difference in the scale and or geometry of the shelf edge data complexes developed under greenhouse and icehouse conditions?" And Gary is from London.
Okay, no, that's a very interesting question. So the general problem we have with the shelf edge delta study is, as I said, like we have very few modern examples, and I have about 40 different deltas, which I have in my study right now. And sometimes the problem is that in the ancient rock record, it's difficult to identify clearly whether it's a shelf edge delta or not, because if the spatial extent of the outcrop, for example, is not big enough or is very complicated because of the tectonic setting, people are not really sure if this is a shelf edge delta or not. So one thing I'm currently looking at as well is I'm looking at facies characteristics, and I'm going to compare them with other delta types. So maybe this might aid in identifying them in outcrop. So that being said, if or when we get to that stage, then maybe I will be able to integrate more data in my current data set, because I fear the way that I have the data now, it might not be sufficient to do these types of analysis between greenhouse and icehouse conditions.
Very cool. And so, Laura, you gave a fantastic presentation. We definitely will return to any questions. We did go a little over time, and I see that we still have a few of the other speakers on here. So I want to make sure we, revisit some of the questions that I wasn't able to get to. So I'm going to scroll back up. If anyone is still in the room who would like to repost their question to make it easier for me, I definitely welcome that. But Liz I see you are still on and it's very late for you, but I did miss some of your questions. So I would love to bring this back up. So I think I missed here Val's for the first one where he said super talk. On the extraction map you showed, are the coal beds the thickest, the closest to the shoreline, or somewhere further away from the shoreline?
Yeah, so that's a really good question. So we know that the coals do thin the further from the shoreline you get, but exactly where the thickest point is in the close to the shoreline part, I think a limiting factor there is well penetration. So unfortunately, in the central deep of the basin, the Paleocene shorelines are, as far as I'm aware, they're the oldest hydrocarbon reservoirs in the basin. And then, so we have the shoreline, which is a zone. And then as you move away from that shoreline, structurally, it dips down into a syncline. So there's a little gap in well penetrations right where we would really like to know what's going on, where those coals are. So I'm not sure that we have the well density enough to do a really detailed thickness map of the coal. It would be really interesting to know though. But yeah, it's a good question.
Okay, and we have one more here, Liz, that I missed. And so it says, great presentation. This is from Unai Obriureta, who says, do the GR neutron of the logs correlate well with the interpretation of the seismic imaging interpretation?
Yep, yeah. So we have pretty good well ties. The resolution of the seismic is not super high. It's pretty coarse at that depth, but they tie quite nicely to the wells and seem to correlate quite well.
Perfect. And Maria Jensen commented and she said, you have amazing data. She'd love to talk about it more because she's working on some similar things in the Arctic. And she asked, have you looked at the paleoterrain? Is it a flat plain or do you have heights?
Also, really good question. I've not looked at paleoterrain at all. I guess I'm assuming it's pretty flat because it's coaly. And also it was a, rifting post-rift phase of basin development. But other than that, I have not actually, but that's interesting. I hadn't thought about that.
Well, thank you so much, Liz. And so we have some questions for Yannis that I wasn't able to get to. And this one was from Catherine Giles, who asked, she said, thanks for the great and interesting talk, Yannis. Can you tell how quickly these islands became vegetated?
Yeah, thanks for the question. To my knowledge, there are no real, or I know no real observations of how the time span is between formation and vegetation, so to say. However, I would think that once an sufficient area is stable enough, and I've shown that some of these are like constantly evolving. In these cases, it's like almost impossible, I would say. But as I said, as soon as there is sufficient amount of habitable vegetable space, but of area that may be vegetated, it could take place quite rapidly, I would think, and it of course also benefits the actual stability of the island and leads to further accretion.
Thank you, Yannis. And you have another question here from Unai Obriureta, who says, thanks for the presentation. Have you compared actual reef island formations with past reef island formations, such as Cretaceous or Jurassic reef?
No, apparently not. We have focused on the Holocene, so to say, but I would be very interested, of course, into looking into some of this, some of the Jurassic reef island research or reef research in general, and to find some analogs. Of course, that would be awesome. So if anyone has something and some information on this, I would be happy to get that.
And so we have a final question for you here, Yannis. It says, thank you for the virtual travel. Pardon my very newbie question, were the neighboring reefs healthier, i.e. growing faster and more solid during the period of low energy monsoons?
Well, it's possible, I think. So it has been reported, of course, that severe storms have huge impacts on the framework of reefs. However, I would say that in this case, healthy, or in our case, healthy basically means that it has produced sediment that is suitable for the actual reef island formation. And from that perspective, the sea level has basically much greater influence, because once a reef grows towards the sea level, it produces really high amounts of calcium carbonate or carbonate in general. And once it reaches the sea level, it basically switches to lateral growth, which usually is causing a decline or decrease of carbonate production. So there have been some investigations that such stronger energetic events can cause some deficits, but I think the actual role of the sea level is of much greater importance there.
Thank you so much, Yannis. We will go to our last two questions for our speakers, and then we will wrap up. Thank you, everybody, for sticking with us. Laura, this was one I had missed for you, and it says, very impressive work. Do you see any scaling relationship for the canyons and or the deltas as a function of latitude? I think that's a great question.
Yeah, yes, I do. And it's very interesting because they're contrary in different regards. So one thing I found was, for example, that in shelf edge deltas, the width appears to get narrower with increasing latitude. And this I have interpreted to relate to the fact that terrestrial catchments become of less importance the higher in the latitudes we get. So we have fewer precipitation, for example, and smaller fluvial systems. And so we have less sediment transported actually this way. On the other hand, when we look at submarine canyons, we see that the canyon width clearly become bigger with increasing latitude. So this is something I think because of glacial processes. And also we have to see here, I'm talking about the erosional channel form and not about the canyon fill. So here the scale of erosion from glacial processes contribute that we have a really significant increase in width when you look above, I don't know, latitudes of more than 40 degrees, where we're supposed to have had glacial influence on the continental margins. And another interesting thing I found was when I looked at canyons in active and passive margin settings, we found a lot of scaling in passive margins, but not in active margins. And this is very interesting and impressive because this shows that apparently the tectonic overprint might have been sufficient that these relationships are obscured. So as I said, so this is something I'm currently looking into. So this is like the last part of my PhD project. And I want to figure out the puzzle pieces between similar and different responses between the two sedimentary systems to environmental controls.
That's fantastic. Thanks so much, Laura. And Liz, I'm going to pull you out one more time for a final question. This is from David, and he says, did you run into any tuning or seismic artifact challenges when interpreting or correlating your seismic facies or depot environments? If so, how did you address that uncertainty?
Yeah, so that is one of the kind of quirks of the basin. I guess it's quite common, but it seems to be particularly bad in the Gibson Basin, is that the coals just blow out the amplitude on the seismic. So coals will show up quite distinctly on the seismic, despite the fact that they're below tuning thickness, which can be a little bit annoying. You do get a little bit of signal attenuation below the coals as well. So I think how I've kind of dealt with that throughout my entire PhD, and with the resolution and variable frequencies using different volumes, is just to keep the scale of my studies larger than the uncertainty. So as long as my analyses are at a broader scale, that kind of gets absorbed into that big scale. I think if I wanted to do any more detailed work, I would need to address it a bit more rigorously. But at the moment, at the scale of my studies, it seems to be okay.
Well, thank you so much, Liz, and thank you to all our fantastic presenters. Those were incredibly interesting research projects, and they look like they're all going fantastically. They're so broad, and we're learning so much about coastal sedimentation. I do want to plug our next one for everybody still here. We're looking at sediment transport dynamics from source to sink. So if you know of any students or any professors who have students, please, please, please send it along. We love to get students involved and open up this platform to them. So thank you everyone for coming, and we will see you next week for our following presentation. And we'll ask our presenters to stay on so we can give them a big thank you.